Hi there. So in this particular video, we're looking at solving systems of linear equations, as well as we'll wrap it up at the end with linear inequalities and linear programming, which is an application of these systems of inequalities and equations. So with that said, we're looking at several sections here, so this video will be a little longer in terms of, because there's a lot of content here to cover. All right, so when you solve systems of equations, there's actually three different methods. There's a method referred to as graphing, there's a method referred to as substitution, and then elimination, and then we can also use the matrix method. So I guess technically there's really four methods for solving these systems of equations. I'm going to show you all of them, all right? So whenever you solve a systems of equations, there are three different scenarios that you can encounter. So the first would be that you would have a system that's referred to as consistent and independent of one another, meaning that if you were to graph them, they're going to intersect at exactly one point. I have a pen here going. They're going to intersect here at exactly one point, and that one point would be your one solution. It may be the case that your system ends up being inconsistent and independent, and if in that particular case, if you were to graph it, they would be parallel lines, meaning they would have no solution. And then the last case is referred to as being consistent and dependent. And what this one is that essentially you'd have two separate equations, but after you solve both of them for y and graph them, you would end up finding that after you graph the first line, when you go to graph the second line, it's directly on top of that line. And so this is the case where you have infinitely many solutions. Okay. All right, so the first method is just graphing. In order to graph something, you always need to solve for y, and then you're looking for your point of intersection. So here in example 1, we're going to solve by graphing. So the first thing I need to do to both of these equations is solve for y. So in the first equation over here on the left, to get y all by itself, I need to take x to the other side. When you cross the equals mark, you have to do the opposite. The x is positive, so I'll subtract x. Negative y equals negative x plus 5. If you're writing 5 minus x, that's the same thing. I just like to get in the habit of putting my x first. Now, we can't leave this as negative y. We need to get rid of that negative 1, so you divide every term by negative 1, so that you are at a negative over a negative gives you a positive 1x, and you don't have to have that 1 there. You can just write x. 5 divided by negative 1 is negative 5, so you have minus 5 there. So that would be our first equation. We'd come over to the second equation and solve it for y. So just one step here. I want to take 2x to the other side, do the opposite. So subtract 2x. In our case over here, that cancels out, and I'm left with y equals negative 2x plus 1. Same thing here. You can write 1 minus 2x. I'm just trying to write it in our slope-intercept form. All right, so now we're ready to graph these. So the first one, if I'm going to graph this by hand, then I would start on remember your slope and y-intercept. So here I would have a slope of, after you solve for y, the number in front of x, so I'd have a slope of 1. I'm going to put a 1 underneath that so that I have a rise and a run. And my y-intercept would be the number that's sitting out here, so that would be negative 5. So remember, y-intercept is where you begin, slope is how you move. So I'm going to begin on the y-intercept down here at negative 5. And then from that point, I'm going to go up 1 over 1, up 1 over 1. And you can continue to do that for as many times as you like, okay? I just did it a few times here just so that I can get as precise of a graph as possible. So I will now connect those dots. Straight line. Now I will go over here and graph the other line. I'll use a different color. Y equals negative 2x plus 1. So thinking about over here, my slope after you solve for y is the number in front of x. So this time you have negative 2. So you have a rise and a run. Remember, it's legal. You can always put a 1 underneath any number. And your y-intercept in this case would be that 1. So 0, 1. So this time I'm starting at a positive 1. And then from that point, I have my negative 2's, and that's my rise. So instead of going up 2, I'm going to go down 2, 1 to the right, down 2, 1 to the right, down 2, 1 to the right, and connect those dots. And if you've been precise in your graphing, you would have been able to identify at this point where they crossed, and they crossed right here at the point 2, negative 3. And so that's the solution to this system of equations. And so what that means is the point 2, -3 satisfies not only the first equation, but it also satisfies the second equation. So like, for example, if you come up here and substitute this in, 2 minus a -3, well, sure enough, 2 negatives side by side turn into a positive, so 2 plus 3, yep, that's 5. And then over here, 2 times 2 minus 3, so 2 times 2 is 4, 4 minus 3 is 1, okay? So that's what it means to solve a system of equations. There's a video in Blackboard that shows you how to do this in your calculator. You have to be able to solve for y, but I show you how to graph this in your calculator and find the intersection, okay? All right, just below here, the substitution method, as I mentioned, is another way for you to solve a system of equations. I'm just going to flip it on over. If you can read through this and read what the steps are. I'm just going to show you the steps. So if I flip it on over to the next page, using the substitution method, to me, I would only use this method if you already have an equation that is already given to you, solve for x or solve for y. To me, that's the best opportunity to use substitution. Otherwise, I tend to go towards elimination. So that will be the one that I focus heavily on in this video, okay? So, but here in example 2, you already have one equation that's already solved for y. So what we're going to do then is we're going to go to the top equation, and everywhere we see a y, we're going to be plugging in 2x plus 3. So I'm just going to write that top equation again. So you have 3x plus 5y equals 2. And so like I said, I'm going to go to this equation, and now everywhere I see a y, I'm going to plug in 2x plus 3. That makes sense? So now my equation is all in terms of the same letter. It's all in terms of x. So 3x, and now distribute this 5, so I have 10x plus 15 equals 2. Combine like terms, 13x plus 15 equals 2. You want to get closer and closer to getting this x all by itself, so subtract 15 from both sides. 13x equals what, -13. Divide by 13, cancels out, so x equals a -1. Your answers to these problems, they're either going to be no solution, infinitely many, or they're going to be one ordered pair. So just because you found x, that doesn't mean you stop. Okay, I found x, but I need to go through the motions and I need to solve for y. The easiest place to solve for y is right here in this bottom equation, because it's already solved for y. So y equals 2 times the x. Well, we just solved for x. We know that x is -1 plus 3. So in the directions that I tell you on the previous page, when I say back substitute, that's what I mean, is you're just substituting the answer that you get into the equation. 2 times -1 is -2 plus 3. -2 plus 3 would give us a +1. So now we know, okay, well, y is +1. So that's our final solution there, the point -1, +1. I just chose to solve this using substitution. If you wanted to solve this using graphing, you could take that top equation, solve it for y, put both of those equations then in your calculator into y1 and y2, and find the intersection. Regardless of how you do it, you're going to arrive at this answer here, -1, +1, okay? So and like I said, if you're not familiar with how to do that in your calculator, I provided a video for you attached there in Blackboard just underneath this video, okay? All right, so now we're moving on to the third method for solving a system of equations, and it's the most widely used method, and it's referred to as the elimination method. And you're doing just that. You're trying to eliminate one of your variables. But in order to be able to eliminate one of your variables, I'm going to draw your attention down here to the bottom of this page, you need for this down here in the box to happen. You need to have the same variable, so I need to have the same letter with the same coefficient, but they need to have opposite signs. And once you establish that goal, then you're going to be able to add down and eliminate, okay? So, and I talk you through that up here in these steps, but I'm going to show you those steps down here below. So what I always ask myself, when I look at a system of equations here, and whenever you use elimination, it's best used whenever they are in standard form, meaning x and y are on the same side. So you'll notice here in example 3, 4, 5, and 6, all of these equations are in standard form. X and y are on the same side, and they're equal to some numbers. Okay, so elimination is best used for standard form. You choose a variable to eliminate. Sometimes that variable's kind of already been established for you, because if you look here in example 3, if I just say, okay, well, let me get rid of my x's. Notice here I've got the same variable, so I've got the same letter. I've got the same number. They're both 3's. One's positive, one's negative. That's my goal for elimination. You know, I could work with my y's here. I have the same letter. I don't have the same numbers. They are opposite signs. So I would have to do some work if I wanted to get rid of my y's. I'll show you how to do that work on another problem here in a moment. But whenever you have a problem that is already sitting here basically ready to go, just go with it, okay? And what I mean by being ready to go is that our letters here are the same, our numbers are the same, and they have opposite signs. So what that means is that I can add down. If I add down at the moment, what happens to those x's? They would cancel out, because 3x minus 3x, that's 0. So they're going to cancel out. 4y minus 5y is going to give you negative 1y. Negative 2 plus 1 gives you negative 1. And then lastly, to get y by itself, divide by negative 1. So y equals a positive 1. Now from here, it's just like before, your answers have to be ordered pairs. So you found y at this point, but we've got to go back and we've got to find x. You can substitute that y into the top equation or the bottom equation. It's entirely up to you. I'm just going to use the top one, okay? So I have 3x plus 4. Oh, I see a y, so in place of y, I'm going to put 1 equals negative 2. And I just keep working from here. So 3x plus, we know 4 times 1 is 4. Get closer and closer to solving for x. I'm going to take 4 to the other side, crossing that equals mark, so I have to do the opposite, subtract 4. Cancels out. 3x equals negative 6. Divide by 3. So x equals negative 2. So your answer here would be negative 2, 1. I'll say this again, you know, I've shown you how to do this with elimination. You can also, if you wanted to solve the system equation using graphing, you could take both of these equations and solve for y, and then if you put it in your calculator and found the point of intersection, you would find it to be this particular point. You will be expected to be able to solve using elimination, so be sure that you do get this method down, okay? And I've provided you with a link. If you need additional practice, you have some of that in your homework and stuff to work with as well. Okay, so let's scoot on over here to example 4. In example 4, this one's a little different. Okay, you'll notice here, you know, if you choose to get rid of your x's, I can't just add down because they're not the same numbers, and they definitely don't have opposite signs. Now if I look at my y's, I have the same letter. They're not the same numbers, but they are opposite signs. So y might be a better variable to get rid of this time, because I've got the same letter, I already have opposite signs. I just need to tackle getting these to be the same number, okay? So in order to get them to be the same number, that sometimes requires you to multiply one or both of your equations by a particular value in order for it to cancel out. So since this equation on the bottom has a negative 4y, in order for my y's to cancel out, I would need this top y up here to be a positive 4. Well, if there's an imaginary 1 sitting up here already, then what do I need to multiply 1 by so that this becomes a 4? I have to multiply it by 4. So we take that top equation and multiply it by 4, and look what happens. You have 24x plus 4y equals 4. And then on the bottom, 3x minus 4y equals 23. Now notice, same letter, same number, opposite signs. So at that point, I'm ready to add down and eliminate. Because, if you'll notice, okay, what can I eliminate this time? Eliminating my y's, right? So 24x plus 3x will give me 27x. 4 plus 23, 27. Divide by 27. So x equals 1. So you've got half of your answer. We know that x is 1. We need to solve for y. You can use either equation that you like. Maybe I'll just go back to that top equation. So it was 6x plus y equals 1. We know that x is 1. So 6 times 1 plus y equals 1. Or 6 plus y equals 1. To get y all by itself, subtract 6. So y equals -5. So our answer here would be 1, -5. Let's talk again about, hey, you can still check yourself on these problems as well. You go back, but you need to plug it into both. So you go back everywhere you see an x, you plug in 1, y's become -5. So on this top one, 6 times 1 is 6, minus 5, that would give me a +1. On the bottom, 3 times 1 is 3. You're going to have -4 times -5, so that's going to give me a +20. So 3 plus 20, sure enough, that's 23. Okay, so you can always do that to check yourself. We'll move on down to example 5 and 6. So in example 5 and 6, just look at example 5 first. Let's look at in terms of eliminating here. You have, in terms of looking at your x's, you've got the same letter. You don't have the same numbers. You don't have opposite signs. So you might want to say, well, let me look at my y's. Same letter. I don't have the same numbers. I don't have opposite signs there. So it's entirely up to you at this point which letter you get rid of, because you don't have an advantage. Like on the last one, we had an advantage because at least with our y's, I had opposite signs already. Okay. Another advantage that I didn't point out with the y's is that the top one had a 1 associated with it, and any variable that has a 1 associated with it is the easiest to multiply by. So that would probably be my recommendation down here in example 5, is that let's get rid of our x's. And in order to get rid of our x's, well, if this bottom down here is +2, then what do I need to multiply this positive? We know that the top up here needs to be a -2 in order to cancel out. So what do we multiply 1 by to get -2? We'd have to multiply it by -2, right? Now notice what happens then. You have -2 times 1, so -2x. -2 times 3, minus 6y. -2 times -4, +8. And then down below, you're just copying, plus 6y equals -8. Notice what happens here. Your x's cancel out. Your y's cancel out. So you're left with 0 on this side. Notice what happens over here. Your numbers cancel out. 0 equals 0. This is a true statement. This is what infinitely many solutions looks like. Infinitely many solutions. In MyLab Math, they're going to require you to write your answer still as an ordered pair. And in order to write your answers as an ordered pair, you take one of your equations and solve it for one of your variables. I always recommend take the equation that has if you have a variable that has a 1 in front of it, take that equation and solve it for that particular variable. So I'm going to take that top equation, x plus 3y equals -4, and I'm going to solve for x because it has a 1 in front of it. So that's just a one step, right? Just subtract 3y. So now we know x equals -3y minus 4. So now if I go to write my ordered pair, then my ordered pair, in place of x, I'm going to put -3y minus 4, and then in the y spot will just be y. I know that looks very different to you, and as far as only reason I'm showing you that, because if like for a test, I would just prefer to be able to say infinitely many solutions, but I know that MyLab Math requires you to write it as an ordered pair. At least I'm pretty sure that they do, and so I just wanted to show you how to do that. And I'll show you again here in the notes. Whatever variable has a 1 in front of it, take that variable and solve it for that letter. Then, here I've solved for x, so that piece there then needs to go in the x spot of your ordered pair, because remember, ordered pairs are always x comma y. And then, so then the in place of the y spot, it would just be y. These two, your ordered pair here, always needs to be the same letter. Okay, so all right, we'll do another one, so you'll be sure that you see another one of those. Okay. All right, so let's look over here at example 6. Here in example 6, let's ask ourselves, okay, if we were to add down, would we have a letter cancel out? And sure enough, in this case, we can stop right here at our x's, right? If we add down, our x's cancel out, so I don't have to do any multiplying or manipulating here. When I add down, my x's cancel out, but look what also happens. My y's also cancel out, so I'm left with 0 on this side, And then 7 plus 5 is 12. So very similar, back before, we talked about when your letters cancel out and they equal each other, you have infinitely many solutions. When your letters cancel out and these numbers don't equal each other, hopefully you recall, this is the no solution. So, and that's the only way to write those. Okay, so you're free on that one. All right, so let's flip it on over. Let's put an application to this. So here in example 7, it tells us that we have 2 hockey tickets and 1 basketball ticket will cost a little over $126. 1 hockey ticket and 2 basketball tickets cost a little over $128. They want us to figure out with this information, how much does 1 hockey ticket and 1 basketball ticket cost? So we'll set up our system of equations from the information given. They tell us, and I'm going to use intuitive letters here. It tells us 2 hockey tickets and 1 basketball ticket cost $126.77, while 1 hockey and 2 basketball cost $128.86. Okay. Now it's entirely up to you whether you want to get rid of your H's or your B's, and I just chose to use H and B so that because I know that it's asking me to find the price of the hockey ticket and the basketball ticket, and so I just want to whenever I find H, I'm going to know that's the price of the hockey ticket, and I won't have to think about, oh, was X hockey or was X basketball? Okay, so and actually we'll come over here already. Let's do this: hockey, basketball, so that we have that ready for us. All right, so in order to solve this system, then we'll need to, we can kind of eyeball it here. If you were to add down, the H's aren't going to cancel out, the B's aren't going to cancel out. I don't even have opposite signs. So but you do have 2 good options. You can choose to get rid of, let's I can't, sorry about that. You do have 2 good options though, because you have a 1 in front of your H, you could choose to get rid of your H's. You've got a 1 up here in front of your B, so you could choose to get rid of your B's. So I'm going to choose just to get rid of the H's. This is entirely up to you though. In order to get rid of the H's, the top up here is a positive 2, so that means I would need this to become a negative 2. So what can I multiply 1 by to get negative 2? It have to be negative 2, right? So my pen. There we go. And now I'm just going to copy the top one over because I haven't manipulated it in any way. So 2H plus 1B equals 126.77. On the bottom, negative 2H minus 4B equals negative, and I'd have to throw that in my calculator. And you should get negative 257.72. Now when you add down, you'll notice my H's cancel out. 1B minus 4B, negative 3B. Equals a negative 130.95 divided by negative 3. So then B, basketball ticket, a negative over a negative gives you a positive. That's good because remember you're trying to find money. Money doesn't make sense in most cases. I guess technically the price of something wouldn't be negative. Okay, you could owe somebody something and that would be a negative value, but the price of something shouldn't come out negative. So B here should come out to be $43.65. So for my basketball ticket, $43.65. To find my hockey ticket, I can plug it into the top equation or the bottom equation. It's entirely up to you. I think I'll just use that top equation. So the top equation is 2H plus 1 basketball. So we just found that basketball ticket to be $43.65 equals the 126.77. Solve for H. So I subtract $43.65. 2H equals 83.12 divided by 2. So hockey ticket is 41.56. Final answer. That would be our final answer over here. Okay. All right, so if we scoot on down then below that, you'll notice here that systems of equations, so far everything we've looked at have been 2 equations, 2 unknowns, but it's possible to have, as you see here, 3 equations, 3 unknowns. Solving these systems of equations, you can still do this by hand, and actually I used to teach it years ago. I used to make my students do it by hand. I won't do that to you guys anymore. We'll use matrices to solve these. So that would be good for you. We'll move on down then. Let's talk a little bit of an introduction here to matrices. In the calculator video that is attached to this set of notes, you will find me walking you through all of the steps for putting this in your calculator. Here in this video, all I'm going to do is I'm going to show you the setup and how we come to know that that is the setup, and then I'll show you in the calculator video how to put it in your calculator. All right, so matrices are always denoted by the number of rows or by the number of columns. Okay, so here on the left-hand side, they're asking us to write the coefficient matrix. So the coefficient matrix are just the numbers that are in front of your variables. So here, our coefficient matrix would be 1, -2, 3, -5. And matrices are usually in the brackets like this. And what we've done here is I've lined up my x's in the first column, y's in the second column. And we would say that this matrix has 2 rows and 2 columns. So it would be referred to as a 2 by 2. You have to know the dimensions of your matrix because your calculator is going to always have you input the dimensions before it will allow you to enter the matrix itself. So you have to know what the dimensions are. Let's do another one. Now, just over here to the right, I say, well, let's write the augmented matrix. And what I mean by the augmented matrix is it puts together the coefficient matrix along with the right-hand side over here. So if I construct this one, I still have my 1, -2, 3, -5. But this time I add another column of 2, 9. Excuse me. So in this case, you can kind of, I'm going to just draw a vertical line here. These are your x's, these are your y's, and these are your constants. Okay. And now if you think about your dimensions, how many rows do you have? Hopefully you would agree you have 2 rows. So the dimensions here would be 2 by. How many columns do you have? Hopefully you would agree you have 1, 2, 3 columns. So this would be a 2 by 3 matrix. Okay. So now down below here I say, given the augmented matrix, write the system of equations. So they're telling us that this is an augmented matrix. So what that means, if it's an augmented matrix, then this last column is always where this indicates your equals. Okay. And because it has 3 columns, then we're thinking about this is an x, a y, and a z. So if I were to now construct what the system of equations would be from this, then that first row would be 3x minus y minus z equals 7. Of course, I can put 1s in front of that y and z if I like. 2x, I don't have any y's, plus 2z equals 8. Y plus z equals 0. Okay. Now, just below that, we're going to look at what's referred to as row-reduced echelon form. And what row-reduced echelon form does is it actually solves your system of equations for you, and it performs behind the scenes what are referred to as row operations to obtain ones along the main diagonal. And so what that looks like is that row-reduced echelon form is going to look like this. You're going to have 1s along the main diagonal, and then you're going to have a triangular set of 0s on the top and bottom of those 1s. And then you're going to have, I'm going to put an A, B, and a C here, and so what that means then is that here's your X, your Y, and your Z. And so it's telling you, in this case, in the first case, X, no Y's, no Z's, so X is A, Y is B, and Z is C. So here, A, B, and C are just numbers. Okay, so they're just real numbers. Okay, but it's telling us that X equals A, Y equals B, and Z equals C. We will be doing, I will show you in your calculator that you have a function referred to as RREF that will allow you to input this and solve it behind the scenes. And so your calculator will turn a matrix like this into a matrix like that, where you have ones along the main diagonal, zeros everywhere else, and that last column will be your solutions. Okay, so let's look at example 9. So we're going to use our calculator in order to solve this. I think what I'll do is I will do one here with you, but I have already created a video that shows you how to do this over and over again. So if you don't follow me the first time, pull up that other video so you can watch me do it multiple times. So what you're doing here is that you are going to be in your calculator. You're going to use the function RREF, row reduced echelon form. It is going to take your augmented matrix. So our augmented matrix is 1/2, 1/3, -2, 1/4, 2/3, -5/2, and turn it into a matrix that has ones along the main diagonal, zeros in these spots, and then this column here is going to be your solution once we perform this operation on it. So let's go to our calculator. Your matrix function is second and your x to the -1 key. You're going to arrow over to edit, hit enter on A. That matrix, if you recall, it had 2 rows. So hit a 2, hit enter, and it had 3 columns, hit enter. And then your calculator then generates for you the number of spots that you need. Then you start entering in your values. So you type in 1/2, so 1 divided by 2, hit enter. 1 divided by 3, hit enter. I talked to you in the previous video, like don't try to, I don't want you to hit 0.3333. You need to actually type in 1 divided by 3. Your calculator, while it looks like it's rounding here, it's keeping all of those numbers behind the scenes. And then -2, hit enter. 1/4, so 1 divided by 4, 2 divided by 3. Likewise here, be sure you type in 2 divided by 3, and then -5 divided by 2. Okay. I'm going to hit second mode to get out of there. Then I'm going to go back to second matrix. Just arrow once over to math. Then you got to arrow down to RREF. It's letter B down there, RREF. Hit enter. Then you want to RREF matrix A. So I'm going to hit second matrix. Hit enter on A. And you can close the parentheses or you can just go ahead and hit enter. And so you can see that it's created ones along the main diagonal, zeros everywhere else. So it's telling us here x is -2, y is -3. So go back to our notes. So this is what our calculator just gave us. It said, okay, well, when you RREF that augmented matrix there, you end up with this 1 here, 0, 0, and then you had -2, -3. So you kind of think about, okay, here's your equals mark, and so we're saying then it's a little bit bigger. So x equals -2 and y equals -3. So you can just write the order pair, -2, -3. Okay. So what might be a good thing for you to do at the moment then is to pause the video and construct what you would RREF over here. Construct your augmented matrix, essentially. Okay. So I'm going to go ahead and do that. I would RREF over here. When you go to put this in your calculator, you're going to RREF this one, this entire matrix here, dimension-wise. Think about it, has 1, 2, 3 rows, so this would be a 3 by 4. Okay, because it has 3 rows and 4 columns. So you would RREF this particular matrix, and you should arrive at the solution. It should look like this: 1, along the main diagonal. You get those perfect triangles in this one, and then you have 1, 3, -2. So here we know then that x is 1, y is 3, z is -2. Final answer. Okay. Flip it on over. I know that I talked about number 11 and number 12 in the calculator video with you. So the only thing that I will say, I think, I can't remember how far I went in number 11, but number 11, because you end up with, I can't remember what I did, so I'll just go ahead and say that after you RREF the augmented matrix, you get this matrix: 1, -1/3, 7/3, 0, 0, 0. And so this tells you, okay, I didn't get ones along the main diagonal here. This is your case where you have this is your special case. You then look to this bottom 2 entries here, and 0 equals 0, right? 0 definitely equals 0. So this is your case of what infinitely many solutions look like, okay? So then all that needs to happen from here is I need to take one of my equations here and solve for x or y. So what I can do then is I can take probably the best thing to do then would be to take that top equation. You take your top solution here, x minus 1/3 y equals 7/3. And just solve it for x, because that's the variable that has a 1 in front of it. And so if you solve it for x, you'd be adding 1/3 y to it. So x equals 1/3 y plus 7/3. So remember, it's writing it as an ordered pair. So your ordered pair would be 1/3 y plus 7/3, because that's what x is. And then you're going to put a y in the y spot. This is, you remember, your ordered pairs are x comma y. Okay. You really have a lot of options. You know, another option that you could do is you could go back to the, once you find out it's infinitely many solutions, you could go back to the original equation here and solve this equation for the variable that has a 1 in front of it. So I could take that top equation, 3x minus y equals 7, and solve it for y. So I'd subtract 3x from both sides. Negative y equals -3x plus 7, then divide everything by -1. So y equals 3x minus 7. Ordered pairs still have to be x comma y, so this time you're saying, okay, well, in place of y, you're putting 3x minus 7, and then this will be x. You just have to make sure that both ordered pairs have the same variable. Okay, so but always solve for the variable that has a 1 in front of it. That makes it a lot easier. Okay, and I know that's the hardest part there with those infinitely many solutions, is getting that final solution in that particular form. All right, and then the last one, I'm fairly certain that I talk about this in the video also, but when you RREF on this one, you end up with another matrix that does not quite turn into your row reduced echelon form. You'll see here, your dead giveaway is when you don't end up with ones along the main diagonal, something's happened. Like I said, always go to those bottom 2 entries here, and here you're looking at 0, definitely does not equal 1, so this is the no solution case. I just wanted you to see, you can still solve special cases using matrices, and I wanted to show you, what does that look like in your calculator. All right. Example 13, I just have you looking at another application, but this time this is actually real application data that I pulled from the Cape Fear website. It actually it's real data, and it so I just wanted you to see like a real application of something that relates here to our system of equations. So the Sea Devils had an exceptional 2018-2019 men's basketball season. Out of the 33 games that they played, they won 27 of those. So after further reviewing their season, it was found that they won 90% of their home games and 78.3% of their away games. They want us to use this information to set up a system of equations, and they want us to find out how many home games and how many away games that they played during the season. Okay, so we know that they played a total of 33 games. So we know then that our home games plus our away games have to add up to 33. Then another piece of information that they give us in this problem is they give us their winning record. They give us their winning record and they tell us how many total games they won. So we can use those winning records in the games won to write a second equation. So what percentage of home games did they win? 90%. We can't put 90 beside it. We're going to put 0.90, right? We got to change that percent to a decimal. So 0.90H plus 0.783A equals 27. And then from here, I'm just going to have you can set up your, you can solve this by hand if you like, but you could also just use your matrices and set up the augmented matrix and let your calculator RREF it and solve it for you. And I'll let you check yourself by the solution key that's posted online. All right, so last section that we need to look at here will be section 9.7, and this is solving systems of linear inequalities, and then an extension of linear inequalities would be linear programming. You can graph inequalities in your calculator. The only problem that I see with graphing them in your calculator is that it does not provide you with the solid and dashed lines. Okay, so just a heads up on that. So you do have to know the difference between that. All right, so whenever you are graphing an inequality, you're going to replace your inequality sign with an equal sign and graph it like you normally would a regular equation. Because these are linear, they're going to have a slope and a y-intercept. If your inequality sign is less than or greater than, you're going to use a dashed line. If it's equal to, less than or equal to, greater than or equal to, you use a solid line. So hopefully that's very intuitive for you, that if it's just less than or greater than, it's a dashed line, and that if it is equal to, that's whenever you get the solid line. Okay. Then what's going to happen is that your graph is going to be divided into two parts, and you will choose a test point. I'm going to show you the test point method the first go around, but then I'm also going to show you hopefully an intuitive way as well, so that you would not have to rely on the test point. So we'll flip it on over. In number 14, it wants us to graph this inequality. Notice here it's already solved for y, so it's ready for us to graph. We can identify our slope and y-intercept. So our slope here, number in front of x, is 1, so 1 over 1, and our y-intercept, where we're going to begin at -3. So I start down here on the y-axis at -3, and from -3 I go up 1 over 1. And we'll just do that a multiple times just so that I get a nice graph here. And then because this is strictly greater than, I am using a dashed line to connect these points. So it looks something like that. All right, I'm going to use then the test point method, and that test point method said that you choose a point on either side, because what happened now after we've graphed our line, it has divided our graph into a top half and a bottom half. And the test point method says choose a point anywhere. So I could choose this point down here if I wanted to, 5, -5. But I could also choose 0, 0. And think about an easy number to plug into an equation, 0, right? So if you can ever use 0, 0 for your point, pick it as your test point, okay? So what that means is I'm going to plug 0 in for y and 0 in for x. And I'm just plugging that into my equation there. Is 0 greater than -3? Absolutely, it is. So since that's a true statement, I'm going to shade where that point is. And so that means I get to shade all the way above up here. Okay? What that means in terms of you know, and I guess, let me back up. So I've shaded above here because that's where my test point was. That was a true statement, so you shade where your test point was. If this had been a false statement, then that meant then I was going to shade on the other side, because then that was not a true statement. So you always shade where it is a true statement. So since 0 is greater than -3, I shaded where my test point was. If that had been a false statement, I would have shaded down here below. To me, an even, a quicker way to do this shading, this is greater than. After you've graphed your line, what makes more sense? Which is greater than then, do you think? Is that above or below the line? And hopefully you would agree that that's above. And so it really is that simple, okay? So if, I'm showing you the test point, so that's your fail-proof way to, be very methodical about where you're shading. But you can always, after you solve for y, if it's greater than, you're shading above. If it's less than, you're shading below. Let's scoot on over here to example 15. Example 15, first thing I need to do here is I need to solve for y. So if I solve for y, first thing I would do is subtract 4x. So I have 2y is less than negative 4x plus 8, and then I'm going to go through and divide everything by 2. So I'm going to have y is less than negative 2x plus 4. So here I have a slope of negative 2 and a y-intercept of 4. So I'm going to start on the y-axis up here at 4, and then from that point I'm going to go down to 1 to the right, down to 1 to the right, down to 1 to the right. It is, again, strictly less than, so another set of dashed lines. I'm going to show the test point method one more time. Test point again, 0, 0 would be a perfectly good point to put in because my line does not go through that point. So I plug in 0 for x and y. So you think about this, you have 4 times 0 plus 2 times 0 is less than 8. Well, anything times 0 and add plus anything times 0 is still going to be 0. So is 0 less than 8? Absolutely. So that means I get to shade where my test point was. If it was false, I'd be shading on the other side. Now think about this the other way. Over here, this is y is less than negative 2x plus 4. Think about here's your line running through here. I would consider everything over here to the right. This would be above, and everything over here down below. This would be below. Everything to the left here would be below. Sorry, this video has gotten long on me. And so anyway, less than, so I'm shading below. Okay. Over here, greater than, so I was shading above. Less than, so I'm shading below. I will come over here just to show you once in your calculator. If you go y equals, clear this out. Up here at the top, if I wanted to graph that last equation that I just did, actually in your notes, was that less than or equal to? I've got some discrepancy on my notes. Well, this is showing less than. If your copy says less than or equal to, it should be a solid line. I'll have to go back and double check that for myself. I'll just correct it so it matches the video here. All right. Go back to my calculator. All right. So if I want to graph that last line there, it was y equals negative 2x plus 4. And then if you graph it, that's all you're going to see. Calculator's not going to give you the dashed line for you. Go back to y equals. Calculator can do the shading. Since it's less than, what you do is you use arrow over here to the left, hit enter. You can change the color if you want to, but I'm just going to arrow down and change the line. It says use your left and right arrow keys. I'm going to use my right arrow key since it's less than. This is the upper triangle, so that would be for greater than. So if it was greater than, you just hit enter here. I'm going to go one more time. It's the lower triangle, so that means less than. And then I'm going to come down here and hit enter. Now when I hit graph, you'll notice that it's showing, okay, that's where we were supposed to graph. It's showing you the correct shading. Okay, so hopefully that helps you there with that shading. All right, so now let's move on down here to example 16. In example 16, it wants us to graph this system of inequalities. So you've got a full 4 sets here. The top ones, I always call these constraints. So the top one says x is greater than or equal to 0. So you're looking at the line x equals 0, and hopefully you remember that the line x equals 0 is actually the y-axis, right? That it's actually this line right here. So that's the line x equals 0. I'll graph it there. That's the line x equals 0. The line y equals 0 is actually the x-axis. That can be a little confusing there. That's the line y equals 0. In both of those, it says it's greater than or equal to. So think about it. For your x-axis, if you want to be greater than or equal to, would you be shading to the left or to the right? And I said for the x-axis, for the line x equals 0, in order to be greater than or equal to 0, you would need to shade to the right. So everything over there. The next one, y greater than or equal to 0, so that's my horizontal line here. think about greater than. Should that be above or below the x-axis? And that would, hopefully you would agree here, that would have to be above. My point in saying all of that is that anytime, and our final answer here is going to be where all four of these constraints overlap in our shading. Anytime you see these top two constraints, that is automatically putting you in the first quadrant. It's telling you, okay, your answer has got to be somewhere over here in the first quadrant. So I am, I graphed the full lines for you, but, essentially at this point, I am only concerned about, okay, what's here in the first quadrant. Okay, so now let's add some more to this. I'm going to need to take these bottom two lines here and solve for y. So I have x plus y is less than or equal to 4, and 2x plus 3y is greater than or equal to 6. So, excuse me. All right, so now what I need to do is I need to take these equations, solve for y, so I can just subtract x. Y is less than or equal to negative x plus 4. So now when I go to graph that equation, I have positive 4. And from that 4, I go down 1 over 1. I'm just, I'm going to erase that. We know, so you're going to get with me now that I'm in the first quadrant. I'm going to erase that, so I've got some less going on here. Down 1 over 1. All right, so now, and I'm connecting that as less than or equal to, so that's a full solid line. Now think about it. It says less than or equal to. Would I be shading above or below that blue line? Hopefully you would agree. I'd be shading below, so I'm just going to do a little arrow there. It's telling me, okay, go there. So now what I'm saying is that my answer is right here in this triangle somewhere, okay? Now let's come over here and let's solve this one for y. So subtract 2x. 3y is greater than or equal to negative 2x plus 6 divided by 3. So y is greater than or equal to negative 2/3 x plus 2. All right, let's go to graph this one. Use a different color. I'm starting here at positive 2, and then from that point, I'm going to go down 2 over 1, 2, 3. Down 2 over 1, 2. Do that right. Down 1, 2 over 1, 2, 3. Okay. There's my green line. Now from that green line, it was greater than or equal to, so that tells me that I'm shading above or below that green line. Greater than or equal to, and that was a solid line because it was equal to. Means I'm shading above, and so hopefully you'd agree then. Now, okay, well, my overlapping then of all four of these constraints is happening here in this area right in there. That would be our final solution. Okay. All right, let's flip it on over. The applications of these systems of inequalities are what are referred to as linear programming. And linear programming is oftentimes utilized with companies. Like think about something as simple as UPS and FedEx, for example. They are especially right now with the amount of packages that they're delivering to folks, the demand. They've got to make sure that they're not willy-nillying in their delivery. And what I mean by that is, if they've got packages that need to go to Burgall, Leland, Wilmington, they don't need to start their morning in Burgall and then come to Wilmington and then, oh, now here's another package. Let me go back to Burgall. And now let me go to Leland, come to Wilmington, and then, oh, let me go back to Leland. You see what I'm saying as far as they would need to be able to maximize their profit, maximize their amount of packages that they can get delivered in a day. That would be an application of linear programming. Now, I will tell you this, linear programming is an extensive topic. I have spent an entire course at UNCW, so that means I've spent an entire semester just on linear programming. So it's vast. You are just seeing a small taste of it here, okay, in this particular section. All right, so so the first one is really just to give you the bones of linear programming, and the second one is an application. So the first one here for all linear programming linear programming problems, you're always going to be given what's called an objective function. And the objective function will be that you are trying to maximize or minimize something. So here we're trying to maximize this function here. Again, it doesn't particularly pertain to anything. I'm just trying to get you the mechanics of how to solve a linear programming problem. So you'll be given a function, an objective function to maximize or minimize. Then you will be given constraints. Usually with a actual problem, though, you would have to devise. You would have to read the problem and actually create the constraints from the wording of the problem. But here the constraints are given to us. We've got 3 constraints. Then after you graph it, the graphing is going to create, I'm going to come back over here to that last problem that we did. It's going to create points where the boundaries of those points, and the boundaries of those points are going to be the points that we're interested in figuring out which one of those points creates the maximum or the minimum, that whatever it is that we're trying to maximize or minimize. Okay, so what needs to happen then is we need to go through and start graphing these. So the first one is the line y equals 2, because remember, you just kind of ignore the fact that it says greater than or equal to at a moment. We want to graph the line y equals 2. So if I want to graph the line y equals 2, I come up here on the y-axis to 2. The only way I'm going to be able to see that line is to go horizontally. Okay, so that's why a minute ago when we said y equals 0 was the x-axis. It's greater than or equal to, so I do get a solid line. So I graph a solid line here at y equals 2. Let's go ahead and keep track of our shading here at this point. It's greater than or equal to, so what makes sense? You're going to shade above or below that line. And hopefully you'd agree. You'll be shading above. I'm just going to use arrows just because to kind of keep it clean, okay? I'll do my shading at the very end. I'm going to get my pen a little bit smaller too. All right, so now the next one. This says that x is between 1 and 5. So it's like looking at the line x equals 1 and x equals 5. So it's looking at those two lines, and we're going to be shading in between them. So the line x equals 1, so here's your line x equals 1, and here's your line x equals 5. X equals are always vertical lines. And they were equal to, so they're both going to be solid lines. And as I said, since it says x is between these, then that means that we are shading in between. So we are shading this way. So now we can already see that our solution is somewhere up here in this much smaller piece now, okay? Because that's right now, that's where the two constraints are overlapping. All right, let's go to our third constraint. The third constraint says that it's this equation here, y is less than or equal to x plus 3. So it's a linear line. So I'm just going to think about, all right, my y-intercept is up here at 3. And then from that point, I'm doing my slope. So 1 over 1, I'm going up 1 over 1. And I'm just going to continue to do that for as many times as I can, just so that I get a nice intersection here. And then it was also equal to, so I get a solid line. Now let's think about our shading here. This one says less than or equal to, so what makes sense? Would you be shading above that line or below that line? And hopefully you would agree that you'd be shading below. Now notice, I'm going to highlight these here. Hopefully you would agree that my shaded region now intersects right here in this piece, and I'm going to come through and I'm going to highlight these 4 major points here. Those are going to be the 4 points that I'm going to test into my maximizing equation here to figure out which one of these is the maximum. So the first order pair here is the point 1, 2. Another boundary point is the point 1, 4. Come over here, I have the point 5, 2 and 5, 8. This 3x minus 2y, again, that's your objective function that you're maximizing. You're substituting x and y, so it's like 3 times 1 minus 2 times 2. So 3 minus 4, that gives us negative 1. 3 times 1 minus 2 times 4, so 3 minus 8, that'll be negative 5. 3 times 5 minus 2 times 2, so that's 15 minus 4, which will be 11. 3 times 5 minus 2 times 8, 15 minus 16, that'd be negative 1. So, since you're maximizing, you're looking for the highest value in this list, and hopefully you would agree that highest number there is 11. So we reach a maximum of 11 at the point 5, 2. Okay, that's the idea of using linear programming. All right, so let's finish this up. I promise this is the last question, but it is involved. So looking down here in example 18, it says a farmer has 70 acres of land available for planting either soybeans or wheat. The cost for preparing the soil, work days required, and expected profit per acre for each type of plant, each crop planted is noted below here. So they tell us that, here are the costs associated with soybeans and wheat, here are the number of work days required, here's the profit that you get. All right, here's some other information. The farmer can't spend more than $1,800 in prep costs, and he can't use more than 120 work days. They want to know how many acres of each crop should be planted to maximize his profit, and they want us to find the maximum profit. So let's go ahead and identify the objective function here. Our objective function is that we want to maximize our profit. And so our profit function is equal to, that's coming from our last equation here, your profit function, 180. I could use S and W, but because I have to graph, I think it's easier to keep it in terms of X and Y. So I'm just going to come up here and I'm going to assign soybeans to X and Y to wheat. Okay, so 100X plus 180X, excuse me, plus 100Y. That's what I'm trying to maximize. Okay, so that will be, at the very end when I go to do my table, like you just saw me finish up at a minute ago, that will be where I end up. Okay. So now let's add some constraints here, okay, for your remember, X represents the number of soybeans planted and Y is the amount of wheat planted. So let me ask you this. Could you have a negative amount of soybeans or wheat planted? Hopefully you would agree. Nope, you can't have that. So two of your constraints are going to be that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0, meaning my final answer has got to be up here in this first quadrant, okay? Now, my next set of constraints have to take into account my prep cost, right? I know the prep cost for soybeans and wheat, and we know that he can't spend more than $1,800. So one of my equations then is going to be that 60x plus 30y has to be less than or equal to 1,800. Okay, that's one of my equations. Next equation is going to take into account work days required. 3x plus 4y has to be, he can't use more than 120 work days. So that's got to stay less than or equal to 120. 120. 0 in there. And then the last one is not in the table, but comes back up here to the first sentence. He's got 70 acres of land available. So he doesn't have, he doesn't have an unlimited supply of land. So his soybean acreage plus his wheat acreage has to stay under those 70 acres. Okay. All right. So now, what I would recommend that we do here in terms of graphing this is let's identify X and Y intercepts. Okay. So like for this first one, if you want to find your X-intercept, then you're letting Y equal 0, and you're solving for X. So like you're doing this, you're saying, okay, well 60x equals 1,800, right? Because you're letting Y equal 0. And then if you solve for X, okay, well then X equals 30. And then if you're going to solve for your Y, then it would be 30y equals 1,800 because you're letting X equal 0 at that point. And so Y equals 60. So then I can say, well, I have an X-intercept of 30 and I have a Y-intercept of 60. Okay. I'm going to just draw myself a line here to keep these separate. The other two, I'm not going to show my work, okay? So, I mean, you kind of get the idea of what I'm doing. If not, email me and I'll show more work. I'll send you a quick video. But all that you're doing here is just saying 3x equals 120 and solving for x. So you should find, and by now you should be, it's the end of the unit, you should know how to find an x-intercept. Solving for x-intercept, you're letting y equals 0 and solving for x. And when you do that, you should get 40 for your x-intercept. For your y-intercept, you should get 30. And then lastly, on this one, X and Y intercept both. Oh. Hopefully you pause this video. I'm getting, I can tell this is definitely a long video. I apologize, but it's just the way that it fell. Your X-intercept is 70, as well as, oh, I just wrote that wrong. See, I told you I was getting tired. 70, and your y-intercept is 70. Okay, again, find your x-intercept, let y equal 0, solve for x. To find your y-intercept, let x equal 0, solve for y. All right, so in order to, I think one more thing that I would be interested in knowing is, if we took each of these equations and solved for y, what would they look like in terms of knowing what you're less than or equal to, or if it ends up changing. So I am just going to go ahead and tell you that I took these three equations here and I solved them for y. So if I took that top equation and I solved for y, you should find that it is y is less than or equal to negative 2x plus 60. I just took each of these top equations here and I'm solving them for y. So if I took that middle one and solved it for y, I'd have y is less than or equal to negative 3/4 x plus 30. And take that last equation and I'd have y is less than or equal to negative x plus 70. All right, so let's start graphing these lines. So the first one, it has an x-intercept. I know these are all 30s and 60s. Let's just take the x-axis and the y-axis and think of these in terms of 10. So like 1 represents 10 and 2 represents 20 and so on. All right, so for the first equation, then you have an x-intercept of 30 and a y-intercept of 60. And we already know that we're constrained here by the first quadrant. I would connect those 2 points. Okay, and then this is less than or equal to, so that's telling me, okay, I'm shading below here. Okay, so that's getting me a much smaller area at that point. Now my next line, it has an x-intercept at 40. I'll use a different color. X-intercept over here at 40, and a y-intercept at 30. Connect that also with a solid line. And it is also less than or equal to, so it's telling me to shade below, right? It's less than, just makes sense that you'd be shading below. So now I'm looking at this region through here. The last one tells me that I have x and y intercepts at 70. So we'll put that one in. 70 and 70. And connect. You'll notice on this one, sorry that's a little wonky there, but in this less than or equal to, this one does not cut us down any further. Okay, so the only thing that needs to happen at this point, if you say, hopefully you then agree, then where my overlapping is occurring, get my pen, my overlapping is occurring then right here in this region. And I actually have 1, 2, 3, 4 points. Let me identify those for you. I've got 0, 0. I've got this 0, 30. That one we know. I've got this 30, 0 down here. This is the one we don't know. We don't know where these two lines intersect. So what I would do is let's go to our calculator and let's let our calculator tell us where these two lines intersect. So calculator, go back to y equals. I'm going to clear that out. You will notice that it did not clear out the less than or equal to over here, so I'm just going to come over here, hit enter on it, come down, and then use my right arrow key until I get back to my solid line. Go back up. There we go. And then hit enter. Enter. All right, so now it's going to be able to graph for us. All right, so we need to graph negative 2x plus 60. Oh, come on. Oh. Negative 2x plus 60 and negative 3/4 x plus 30. If you hit graph, if you're like me, I'm in a standard window, so I'm not going to see the graph at all. That means I would need to adjust my window. A way to sometimes help you in adjusting your window is if you were to hit zoom 0. Zoom 0 is a zoom fit. A lot of times it doesn't fit the way we need it to, but it at least gets you started. And so you'll notice here, okay, well, I'm starting to look a little bit better. I'm seeing that these graphs, that they're going to intersect somewhere. Now ask yourself, think about this. I need to see more of my positive x-axis. So I'm going to go to my window, and if I need to see more of my positive x-axis, then I need to make my x max bigger. And back on our graph, we know that it needs to at least go out to 30. So I'm just going to go out a little higher and go say, okay, let's let our x go out to 40. Hit graph. All right, so now you can see, okay, we're getting a little bit better here. We need to see more down here of our y min. We need to see what's going on down here, the y min. So go back to my window, the y min, and you'll notice here mine is my y min is actually still in the first quadrant, so I need it to go down a little bit lower. So I would probably just say, well, let's just take it down to -10, and then that way you're definitely going to be able to see everything that you need. There you go. Okay, and like I said, we're interested in what is that point right there, because we already know that this is our 30 and this is our 30, but we need to know, okay, what is that? So we're going to hit second trace, number 5 for intersect. Hit enter on the first line because it's right here on my y1. Then it says second curve, then it's up here at y2, so hit enter there. The guess, like I always like to do, is just move my cursor as close to the point that I'm trying to find. Hit enter. The intersection there is 2412. So going back to our notes, we now know that that point there is 2412. So that now if I create an ordered pair or create a table for ourselves, I'm looking at a point. I am trying to maximize the profit, which was 180x plus 100y. That was the very first equation that we wrote at the very beginning here. I'm sorry, this one right here. I'm using that one. And using those 4 points that you see there in the graph where they overlap. So you had the point 0, 0. You had the point 0, 30. Even my pen is tired. It looks terrible now. 24, 12. Oh my. And then 30, 0. Sorry. Just can't help but laugh at this point. All right, so now you're plugging in these values in for X and Y. I've shown all my work on the solution key. I'm just going to tell you, after you plug in 0, 0, of course you're going to get 0. If you plug in 0, 30, you should get a profit of 3,000. 3,000. And if you plug in 2412, you should get a profit of 5520. And then if you plug in 30, 0, you should get a profit of 5400. So therefore, we have a maximum profit of 5520 with 24 acres of soybeans. I mean, really, I don't know why. I don't know why my pen is not working anymore. It's tired, like I said. 24 acres of soybeans. Oh my. And 12 acres of wheat. I'm sure you're having a little trouble reading this. I know that you can see it on the solution key though. All right, I'm finally done. Let me know if you need anything. Thanks a lot. Bye.